Good afternoon and welcome to today's electronic design webcast. Our topic today, automotive in-cabin sensing with 60 gigahertz single chip radar, is sponsored by Texas Instruments. I'm David Moliniak with Endeavor's Design Engineering Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speaker. Dave Woodall is a senior software engineer at Texas Instruments in Dallas. He has years of experience in software programming of low-level drivers, middleware, algorithms, and application software. Dave has been working on developing in-cabin sensing applications on TI's 60 gigahertz and 77 gigahertz single-chip radar sensors. You can learn more about our speaker by clicking on the blue speaker bio widget on your console toolbar. Now let me turn things over to our presenter. Dave, the floor is yours.
Okie doke. Well, welcome everyone, and thank you for joining this webinar on the new TI AWR 6843 devices for in-cabin sensing. Okay, so TI millimeter wave sensors are radar-on-a-chip devices that provide range, velocity, and angle information for detected objects, whether those objects are stationary or moving. This technology works in conditions that are difficult for other sensing methods such as darkness, precipitation, and extreme temperatures. Some of the advantages of the TI millimeter wave devices are that they are a single low-power chip that uses RF CMOS technology. All radar processing is done on the chip, so there's no need for an additional external processor. In the in-cabin space, TI sensors support child left behind detection, occupant detection, vital signs, airbag deployment control, and seatbelt reminder applications. These devices support either 77 or 60 gigahertz frequency bands using the same software environment. The size and single chip design allows for easy integration into the vehicle system with faster time to market for existing reference designs and third-party developers. It is a PPAP-ready, mature solution. Okay, so the two devices that we use currently for in-cabin solutions are our AWR 1843 and our AWR 6843. The primary difference between the two are the frequency band that they operate in. The 6843 operates in the 60 gigahertz frequency range. Besides that, the 6843 contains a newer version of the radar hardware accelerator, which is a hardware-based tool for doing FFTs and filtering and radar-type operations like that. One of the additional features of that hardware accelerator is that it has a memory compression unit, and so that is the reason why there's a 1/4 megabyte less memory on the 6843. The last difference is that the 6843 contains an extra CAN FD, where on the 18 you have a CAN and a CAN FD. So we have built a reference design for vehicle occupancy detection. You can find it on our website at this URL. And we originally built it on the 1642 device, and it is now running on the 6843 device. And I'll talk more about the device and the software in just a moment. all of the algorithms that we use in this reference design are listed in this reference design that's on the web. Again, all the radar processing that is done for the application is done on board the device. We output a heat map and zone decision information, basically. And we have designed a chirping pattern that is tuned for detecting small movements. And we'll go through the chirp in a few slides. So this is an overview of what is present in our design. Again, the AWR 6843 ISK. As we've mentioned, this has got 3 transmit channels, 4 receive channels. It actually has 2 ARM cores that we'll talk about, and a DSP core. And of course, it has the RF front end for doing the analog to digital conversion. Our chirp that we'll talk about is tuned again for very small movements in a very short range. And the one point that I wanted to call out here, we have tuned this chirp to maximize velocity resolution. So as we talk about the chirp, you'll see we talk about range resolution and velocity resolution and angular resolution. And so what we are most concerned with is velocity. So that's the fundamental reason for the selections of the chirp parameters that we have used. In terms of software, all the source code for this program is available in our automotive toolbox, and the automotive toolbox is available in the TI Resource Explorer, which can be found at this website. It's also available within our integrated development environment. We call it CCS, which stands for Code Composer Studio. When you open the Resource Explorer, it looks like this on the bottom left of this slide. You can see that we drilled down into millimeter wave sensors, labs, and then opened up the vehicle detection, vehicle occupant detection lab. And what it shows you in the main pane are the projects that you can import into our Code Composer environment. And it opens another window that shows you the user guide that has all the pertinent information for the demo. This user guide is an HTML file that lives in the docs folder of the source. So I think it's more useful to open it from Windows and where you can view it in a full browser window. It's a little difficult to view it within Resource Explorer, but that's where the software is located. The foundation software that this application is built upon is the millimeter wave SDK. You can find all the installers for the various releases of the SDK at this website here. One thing that I like to note here is that when you run the installer, it not only installs the SDK, but it installs all the component versions that are required by the SDK. And those are like compiler versions and NAT libraries and BIOS and other things like that. So it will install everything that it needs for that version of the SDK, and that's a very nice feature. Okay, so now we're starting to turn our attention into the details of our application. And the first thing I wanted to address was the antenna and the mode of the radar that we are using. This application was originally developed before the 1843 or the 6843 existed. And so that was the 1642 boost EBM. In that EBM, it only had 2 transmit antennas, whereas what we see here in the top, we have 3 transmit antennas on the 6843. So when we run this version of the demo or the program, we are only using the azimuth antennas. And so this is a TDM MIMO application. And so what we mean there is that what we will do is fire these transmit antennas one after the other, and we'll collect all the samples from the receive antennas. So in this case, we'll fire transmit antenna 1. We'll collect all the samples for the 4 receive channels. And because of the spacing between these antennas on the board, spatially, those samples will represent points in the azimuth direction. And so then when we fire the transmit antenna 3, then we get the second set of receive channels. And this forms of what we call a 1x8 virtual antenna pattern. And having 8 antennas in a single plane gives us a very good angular resolution. So, but this is not the only antenna that you can use for in-cabin sensing. What I show on the bottom half of this slide is our 6843 ODS antenna or EBM device. And here you can see that instead of the antennas being arranged in a row, they're now arranged in a 2x2, and the transmit antennas are arranged in an L-shaped pattern. So as we fire each of the antennas in sequence, we build up a virtual antenna array that looks like this. So the first point that comes up is that we don't have as many antennas in the azimuth direction, so our angular resolution won't be as good, but that is compensated for by the fact that we now have elevation information that we can make use of as well. So where we have better resolution in one direction with the one antenna, with the other antenna, we've got azimuth elevation data, or range azimuth and elevation azimuth heat maps that we can build. So looking at the chirp that we introduced a few slides back, what we are trying to achieve with this chirping pattern is a little different than most radar applications. In your common radar type program, you're looking out at hundreds of meters. You're looking for big objects that are moving quickly. And with this chirp, we're kind of doing the opposite of that. We're only looking at a couple meters because we only really care about the inside of a car. And we're looking for things that are moving very little. So our main focus in the chirp is to maximize our velocity resolution. And the way that we do that is by having as many chirps in the frame as we can, and maximizing the time in between the start of each of those chirps. And that maximizes our velocity resolution. The second thing that we want is the angular resolution, and we get that by our 1x8 virtual antenna, or our two-dimensional azimuth and elevation antenna pattern. So the last thing that we can do we need to fit our data into a certain amount of memory. In this case, we set our radar cube at half megabyte. So within that limitation, we try to maximize the range resolution as much as we can. And these are the parameters that we have chosen to do that. So the range resolution is set by the bandwidth that's used. And with this frequency slope, we get almost a 4 gigahertz bandwidth. And that's pretty much the extent of what you can do. What's shown on here on the right is, this is an excerpt from the SDK user guide. And this shows all the different configurable parameters that you can set when you are building a chirp. So in our case, just a couple of the parameters are the idle time. We have a very large idle time, so there's a large dead time between the end of one chirp and the start of the next chirp. And we have a relatively short sampling window because we're only collecting 64 samples. But we have tools, we have sensing estimator tools and all kinds of analysis documentation that lets you, gives you information on how to program this front end. Okay, so now we can start looking at the processing chain that we use in our occupancy detection. This slide is an overview of what that processing chain is. We're going to dive down and talk about each of these things in more detail. What I wanted to show here is the partition of the algorithms amongst the various cores of the device. These devices have 2 ARM cores and a DSP core. And so the first of the ARM cores controls the radar front end. And this ARM core, we as TI provide firmware that runs in this ARM core, and we provide the full API that allows you to configure that front end. But it's a black box. We don't allow users to build and run their own software in this RF front end. All of the processing is going to happen on the DSP. When it gets done, we're going to dump the results in a shared memory, and we kick a mailbox event over to the second ARM in the master subsystem, and then it takes that data and writes it out to the UART. And this happens once per every frame. And in this application, we can run our base application runs at a little faster than 6 frames per second. We can tune our chirp a little bit to run at 10 frames per second, which is something that we do. We have a version of this demo that also provides vital signs, and in that case, we do actually run at a 10 frames per second frame rate. Okay, so drilling down a little bit deeper, the first stage of the processing is the range processing, or we call it the chirp processing. So as we talked before, we are firing these antennas one at a time, and each time that we fire an antenna, a transmit antenna, we are going to collect 4 sets of samples back, 1 set of samples from each of the receive antennas. And for each of those sets of samples, we're going to do a range FFT on that data. So for 1 chirp of TX1, we'll get 4 FFTs, and then with the next transmit antenna fires, we'll have 4 more FFTs, which gives us the 8 virtual channels. We store all this data in a big data structure that we call the radar cube, and it's a 3-dimensional radar structure, which is the foundational structure for all the algorithms that follow the chirping time. And this radar cube, if you look in the SDK, they have defined several different formats of how the data is arranged in the radar cube. But for the purposes of today's talk, it's good enough to know that it's dimensioned by range bands, it's dimensioned by chirp, and it's dimensioned by the number of virtual antennas that you have. So once we have our completed radar cube, we can start with our frame-based processing. And the first stage in doing that is what we call static clutter removal. It happens very often. There are objects in the car that create a very strong radar return. One of these that we've dealt with a lot is the metal seat structure of within the seat backs. Or it can be any kind of object that someone leaves inside the car can generate a strong radar return. So what we are showing in these pictures here, the picture on the left, you see a very bright return. This is seat structure, I believe. And if you look to the left of the gray box, there's a small patch of brighter energy here. And that's actually the person sitting in the seat. And so in this case, before we have run clutter removal, that signature is dwarfed by the return of that seat structure. So following clutter removal, you can see that static object has been removed, and now we have a much stronger signal to the human occupant. So that's the benefit of removing all the non-moving objects in the vehicle. And we do this by subtracting the DC component from all the range bands that were output from the FFT that we did earlier. And this is done for every virtual antenna for every range band. So once we've done the static clutter removal, then we can actually do our heat map processing. And at a high level, what we're doing is we're condensing this large three-dimensional data structure down into a two-dimensional spectrum matrix. In this case, we're doing a range azimuth heat map. So the first stage of that processing is a spatial covariance estimation. We do that by stacking range bands across the antennas for each range band and each chirp. Once we've done that, we run that through an MVDR or Capone beamforming algorithm, and that gives us our angular spectrum data for each of the range bands. And at this point, we've combined all of the virtual channels, all 8 of the antenna data into a single set of points for the range band. And those points are azimuth points in that range band. Once we have the heat map generated, then we can start working on zones. And a zone is an area of the vehicle where you want to pay attention to. And that in our testing we've done, most commonly a zone corresponds to a seat location, but a zone can be like the whole back seat, or it can be the whole back seat and the footwell. It's just some area of interest that you want to monitor. Anything that's outside those zones that you want to look at are not used anymore. So a a way to optimize performance once you have your zones defined. A lot of the heat map processing that was done in the last step can be avoided in those range bands that don't correspond to the zones. The first step in moving from the heat map into a detection is calculating a thing that we call the feature. And the first part of that feature is an estimation of the power of the zone. And we first started doing that power estimation by just doing a simple average of all the cells within that zone. And that works very well. The problem arises, though, that a human signature is going to be relatively constant in the size or the X by Y area of a zone. It's not going to grow or shrink too much. But if you just define a larger and larger zone, then by doing a simple average, what happens is your power estimation gets diluted because you have fewer and fewer points that are the actual signature that you're looking for compared to all the points in the zone. So what we do now is we scan the zone and we find the 5x5 region within the zone that has the most power. And that's what we use for our power estimation. Once you have that power estimation, then we keep a history of those estimated powers for some number of frames in the past. And along with that, we create and store the ratio of power between the zones, and we also create and save the correlation coefficient of the zone power. And so all of these things together are what we call the feature extraction, and that's basically a definition of what the power looks like at the current time of that zone. So from that point, then we do a vector multiply against a set of input coefficients, and the result of that vector multiply is a Boolean array, which says zone 1 is occupied or zone 1 is empty. And so these input coefficients come about by running an offline tool where it's a training tool, so that you stage your vehicle so that you put occupants in certain zones at certain times. Like you'll have a case where if you do 2 zones, you'll have both zones occupied, both zones empty, one zone occupied and the other not, and vice versa. And so the tool takes all of this data that's collected and it generates coefficients that are used. And so it's in effect training the program to know what to look for to make a decision. So when it sees a certain kind of power, then it can say, yes, we think the zone is occupied, or no, we think it's empty. And so this is the result of all of that processing. This is an example of a heat map with a few zone detections. In this case, we've got 2 zones in the front for the driver and the passenger. We've got 3 zones in the second row, and we've got somebody sitting in the passenger seat and in the center back. The first thing that I've been saying heat map this whole time. It's actually not a heat map per se. It has nothing to do with heat. It's actually a velocity map, and the intensity of the colors represents the strength and the amount of movement that has been detected by the NVDR Capone beamforming algorithms. So in this case, we can see the areas of higher power. And if you look close, you can see a little tick mark that's located within those zones. And what that tick mark is the center of where the processing has found the maximum 5x5 power. So it looks a little funny in this back center zone, and what I've done here actually is I overlapped two zones. So that's why you'll see two different tick marks for where it thinks the center of power is for each of those zones. And the nice benefit of doing that as well is that we can output with more resolution the location of the subject in the vehicle. So if we had defined the whole back row as a single zone, we could say, yes, we think somebody's there. No, we don't. And not only that, we can tell you where they are. We can give you a center of the power. So this is one kind of display that we have. We have others that are more pictorial in showing occupants placed in the car. I don't have those handy at the moment. So we've obviously done a lot of testing with these algorithms. What we wanted to show here is our two basic mounting positions of the sensor. This first one is the rooftop position. So in this case, the sensor is mounted in the center line of the vehicle, typically no further front than the back of the front seats, and it can be further back. You can mount it right over the second row of seats. The benefit of this rooftop position is that it gives you very good visibility into the footwell of the vehicle, and it also gives excellent visibility of the entire second row, as well as in some cases the cargo area behind that second row. And in this case, since it's a rooftop position, the sensor has a more downward facing angle to it, and that's what facilitates the wide field of view in this the second row kind of a position. The other position that we've used a lot is more of a front-facing mounting position, and here we can typically mount the sensor either right by the rear view mirror, or sometimes in the headliner just behind that rear view mirror. And so in this case, the sensor has a more horizontal orientation to it. This gives us good visibility over, say, two rows, for example, depending on the mounting position, either the first row and the second row, or the second row and a third row, or a cargo space. If you're interested in doing intruder detection, this also gives you good coverage of all the windows around the vehicle. You can see people coming up from outside the car. So this is another alternative that can be used for this kind of application. And I think yes, that is the end of my presentation. So I guess at this point we can start the question and answer, I think.
All right, Dave, very good. So a few of you have already submitted questions, so we'll jump in. If you'd like to submit a question, type your question into the question window on the side of your screen and then hit that submit button. While we're answering your questions, please complete the feedback form that's located on the bottom of your screen. So let's get started. If we have a question, if a baby doll was used for testing, how did velocity sensing work if the occupant, air quotes, was not breathing?
Well, it wouldn't. If the person doesn't breathe, then if the person is completely still, then you're not going to detect them. And I mean that's abnormally still, right? You would have to hold your breath for some number of minutes for that to happen. But yeah, so if you're testing with the doll and the doll turns off, which happens all the time, you're not going to detect it.
Okay.
I don't know if that answered your question.
Yeah, just want to jump in. So his question was, in this particular baby doll is an electronic doll, which can be battery operated, which simulates the breathing of the baby by expanding and dilating the chest movement. So that is what was used for detection in this purpose. If the baby doll was turned off and there is no chest movement, then the detection won't happen.
Okay, makes sense.
Yeah, and I will add to that in that the doll can be difficult to work with, in that a real baby, for the most part, is going to be moving more than just a little bit of its chest, right? It's going to be breathing, it's going to be wiggling around, it's going to be moving arms and legs and head, and so there's typically more signature available for a real baby versus the doll. But the doll is a good thing to test with because the doll is a stressing case.
Okay, very good. This next question is interesting. Someone's thinking of alternative applications, I guess. Could the system be used to detect occupation of something like a shower room, for instance, in, say, a house for assisted living for people with disabilities?
Yeah, and in fact, we have another demo that it's not the vehicle occupancy demo, but there's a demo in the industrial toolbox. It's called people counting, and it does just that. It detects people in rooms, and it even can track their movement. So that demo does exist already.
All right. Here's another question. Static objects. Will static objects in the back of a car be filtered out after some time, or will such a system always detect their presence?
In our application, we always run the static clutter removal. So we always remove any object that's not moving. That's not to say, you could have an application where you are looking only for static objects. So that's not to say we can't detect them. It's in this application we are trying to eliminate them so that we improve our signal for the moving objects.
Okay. We have an attendee who's confused by the term heat map. Is this or is this not a thermal sensor?
Yeah, and I may have hit on this after the question was asked, but yes, it's a heat map in the sense that it's showing energy, but it has nothing to do with heat. This is not a thermal sensor. It's radar only. The brighter spots, the more energetic spots of the quote heat map are really higher areas of more movement that's been detected. It's a velocity map.
Okay. That makes sense to me. Will shadows from the movement of the sun or objects outside the car cause false triggers?
Shadows will not. Objects outside the car typically do not. It depends on how you define your zones. You could define a zone to be outside the car. So if somebody walks up to the car, it would trigger that zone. So that would be a case of intruder detection. So the answer is it can. Shadows will not. Any kind of environmental, rain, darkness, those kinds of things do not affect the detection in any way. But you can program it to look for things that are outside the car, if you so desire.
All right. We have an attendee asking, is the system able to detect movement through materials, for instance, sunshades, jackets, blankets, dog crates, whatever might be in the car?
Yes, and that's something that we do a lot of testing on. The radar can even penetrate seats. So if you have something in the cargo area and it's blocked by a seat, there are times when you can detect right through the seat. Now, having said that, the more material that the radar has to go through in order to make a round trip back to the radar, the more attenuation you have. So, I mean, things like blankets, thin objects like that are no block at all. There's no attenuation really for those things. Something very thick like a seat, you're going to have a little drop in signal to see those things.
Mm-hmm. Okay. Is the radar system safe? Is there any danger of any kind of RF radiation?
No.
Maybe Dave, I can take that.
Okay.
Sure. Do you want to go for it?
Yeah. So, according to the literature we have studied, we are not aware of any harmful effects of the radiation. In fact, if you look at some of the literature available on site, at the EIRP of 10 dBm, the incident power density is much smaller than 1 milliwatt per centimeter square. So other than that, we are not aware of any other harmful radiation effects. In fact, there's a terminology called SAR, or specific absorption rate, as well. If you just search for it, I think you can get more information.
Okay. This is a question related to the sensitivity, I guess. Can the sensor detect heartbeats and even if it's someone as small as a sleeping newborn, for instance?
Yes, we can detect heartbeats. I think I mentioned that we have another version of this application where we combine occupancy detection and vital signs. And this application works for 2 zones. So it will detect, first of all, if there's a person sitting in the zone, and secondly, it will measure their breathing and their heart rate.
All right. There was you made a reference earlier in the presentation to 5 by 5 or 5 times 5. What is the unit of 5 in that statement?
Okay, so when you generate your heat map, you have a set of range bins. So in our case, we have 64 range bins, and for in the azimuth direction, we've got 48 cells. So our heat map is 48 cells by 64 cells. And so when I'm talking about looking at a 5x5 area, that's cells of the heat map. So I don't know if that helps you or not.
Okay.
But typically, yeah.
No, go ahead, Dave.
I was going to say that typically a zone, well, there's two things. One, a zone is usually at least 3 or 4 times as big as a 5x5, and the signature of an adult rarely exceeds that 5x5 in the testing that we've done, that we've seen. So that's why we chose the 5x5. It's just that's typically the signature size that we see in the heat map.
Okay, sort of a mean or an average, I suppose. Okay, I think I have time for one more. Can vibrations inside the car or normal movements of the car, like bumps or stops, influence the measurement of the sensor?
Yes, it can, and so that those type of vibrations are accounted for by extra processing. And we have this application does not perform those extra processing steps, but we have third-party providers that show this demonstration, the occupancy of a vehicle that's going down the highway or in city streets. So yes, the vibration does have an effect, but it can be filtered out through additional processing.
Okay. Well, I'm afraid we've run out of time. It was a great presentation, lots of great questions asked and answered. If you've asked a question that wasn't answered, we'll be in touch with you soon to answer all of those questions. And that concludes today's presentation. On behalf of Electronic Design, I'd like to thank Texas Instruments for sponsoring today's event, and of course, all of you for joining and participating. Have a great rest of the day.